Okay, thank you very much, and thank you for having me. So yeah, the title, I guess, of this series of lectures is one, delocalization, which is kind of an obscure notation, which I don't know if is very common. But anyway, hopefully by the end of today's lecture, you'll at least know what I mean by this. But let me tell you my goal for this series of talks. Maybe I'll use Spark. So my goal for this series of talks is to show to you how to prove various analytic and geometric inequalities such as, for instance, isoperimetric inequalities, Brunn-Minkowski type inequalities, Poincaré or Sobolev type inequalities, and so on, by reduction to some one-dimensional analysis. Okay, now of course this idea, we've been using it since, I guess, our mathematical childhood. Anytime we use kind of Fubini's theorem, right, that's basically what we're doing. If you're passing to polar coordinates, if we manage to prove some inequality on these one-dimensional rays with appropriate weight given by the radial Jacobian, then we're basically applying this idea. But of course, I would like to present a methodology which enables kind of constructing, or maybe even in a non-exactly constructive way, various other one-dimensional decompositions of your space, more explicit or less explicit, which are problem-specific and which basically reduces the analysis to analyzing what's going on these one-dimensional segments. Okay, now this idea is, of course, very natural, or at least I'll try to convince you that this is very natural from the point of view of optimal transport. So at least in my understanding, there's a big crowd of people here, at least, which are dealing with optimal transport. So we'll see optimal transport as a method to construct such a decomposition of our space into one-dimensional kind of sub-problems appearing in the last talk. Okay, but in the middle, there will be some connection. Well, the connection to optimal transport will be somehow more indirect, less immediate. So I do promise to come back to optimal transport in the last talk, but just not to lose you and to give you motivation, I thought to start with some motivation coming from optimal transport regarding this idea. Okay, so let me try to give you an example of how to kind of make this program work coming from optimal transport. So example from optimal transports. Okay, so of course you guys are the experts, but let me just remind you kind of the basic framework. So assume that you have, let me do everything very simple in Rn, not in full generality. So assume that we have two absolutely continuous, let's say, probability measures. On Rn. Okay. Let's assume that they have finite second moments. Okay, it's not completely crucial. And then, of course, you all know that the Wasserstein distance. Yeah. Okay, so the square root of the Wasserstein distance between mu0 and mu1 is defined as the minimum over all maps, all possible ways to push forward the first measure onto the second measure, which minimizes the L2 transport distance. Okay, so I want to kind of transport my first measure onto my second measure, and the most efficient way when efficiency is measured by the L2 distance cost. And we know already for 25 years, this is a theorem of Jan Brunner, that the Brunner map T indeed realizes, so this is not just an infimum, it's actually a minimum. It realizes this minimum uniquely. Of course, everything is mu0, let's say, almost everywhere. And in fact, there's a beautiful characterization. It's characterized as being the gradient of a convex function. Okay, so this is Brennier's theorem. And now, this is around 1990. And then Robert McCann, around 97, proposes the following idea. So let's take a look at kind of a geodesic in this Wasserstein space. So let's take a look at the density, at the measures which are interpolating between mu naught and mu 1. So I take a look at the interpolating map 1 minus t times the identity plus t times this Brenner map. And I'll call this entire thing, we call this t sub little t. Okay, t is a parameter, little t is a parameter between 0 and 1. And I push forward, I act on mu naught. Okay, and let me call the densities that I get. It's, one can show that our setup is that both of the measures are absolutely continuous. So the interpolating measure, it's enough, I think, just for one of them to be absolutely continuous, so that along the interpolation we get that we're absolutely continuous. So let me denote the density here by phi t. Okay, this is the density with respect to Lebesgue. So this is the interpolation along these one-dimensional transport rays. Right, so the picture is that, let's say I have my mu naught, which is, let's say, sitting here. I have my mu 1, which is sitting there. And this map for any x, my Brenner map, maps x onto t of x. Maybe here I'm mapping here, something like this. And if I'm giving a little parameter, little t, then I look at these t1 minus t interpolation, and I get some measure which is maybe supported somewhere here. Okay, that's the picture. So of course, I'm doing everything on our end. So right now, these one-dimensional transport rays are just intervals. Okay, but later on, we're going to do this on Riemannian manifolds, and then there'll be geodesics, and you can kind of imagine them being curved. Okay, but for now, they're just straight lines. So this is basic. This mu sub t is actually, it's easy to see using, let's say, Brennier's characterization, is actually the geodesic interpolation, the geodesic between mu naught and mu 1 in the Wasserstein space. Okay, so he considers these types of interpolating measures, and he wants to, so Robert McCann wants to study the convexity of some functional. So he gives a definition, functional E of this density phi, maybe some integral of density phi, of some function u applied to this density. This guy is called displacement convex if when we look on, if it is basically convex on this Wasserstein geodesic space. So if we take a look at t going to the function applied to the density phi of t, this thing is convex for any two measures, source and target measures. Okay, so basically we're testing convexity not with respect to the linear structure that we have on densities, right? We can of course add densities, we can multiply them by a positive scalar, but we're not testing convexity with respect to this linear structure, but rather with respect to the geodesic structure given by this Wasserstein space, so along this interpolation. Okay, and McCann's idea, in fact, he gives a characterization. So McCann's characterization of geodesic, of displacement convexity. Let me state this as a general principle instead of writing what the condition on U is. So McCann's principle or characterization is that it's enough to check this displacement convexity along these one-dimensional transport rays by transporting an infinitesimal n-dimensional volume element. So imagine that you have some n-dimensional volume element here. Okay, it's being mapped to this point. So you see that, of course, there is a Jacobian to your map, capital T, and you see what is going on. Maybe it's it's enlarging in this direction. Maybe it's contracting in the other direction. So you want to check the displacement convexity when transporting of an infinitesimal n-dimensional volume elements, which amounts to checking the Jacobian of this map T sub T. Okay? So basically, you want to check the Jacobian, what happens to the Jacobian along these one-dimensional rays, and that's basically a 1D reduction, if you will. You just have to check what happens to the Jacobian along these one-dimensional sub-problems. Okay? And it turns out that the Jacobian here of these maps is intimately connected to the geometry of the space. Right now, we're doing everything in Rn. Yeah?
What is U?
Well, it's some function, scalar function, real value function, which you apply to the density. So in fact, McCann obtains a characterization. This functional is displacement convex if and only if some condition on U, which I don't want to write. It's irrelevant right now. Okay? And basically, this will be the theme for this entire series. So I want to show you how to reduce to one dimensions. And then the analysis in one dimension is already problem-specific. I'll try to cover a wide array of problems, isoperimetric, Sobolev type, Brunn-Minkowski. And then, I mean, the one-dimensional analysis may already be problem-specific, but the reduction as a program is common to many problems. So I don't want to write to you what is McCann's characterization. Maybe a better name is principle. But you can open the book of Villani, let's say the first book, and you see 3 types of different functionals you can study and precise characterizations when these are displacement convex. Okay? So it turns out that this kind of principle, this idea has been very useful. For instance, if you look at some specific functional called the n-dimensional Renyi entropy, it turns out that the displacement convexity of this functional is actually equivalent to having a non-negative, or more generally, some lower bound on the Ricci curvature of your space. So when you start working with manifolds or with more general, you can endow a Ren with a density. You can look at manifolds with the density. It turns out that this displacement convexity is actually equivalent to having this non-negative lower bound of Ricci curvature. And this has been used in various works, celebrated works by Lodge, Sturm, Villani, to actually define what is generalized Ricci curvature bounded from below, or what is curvature dimension condition on a very general metric measure space setting. So this has been very useful. And also, this idea has been very useful. It enabled Dario Cordero, Eroscan, McCann, and Schmuckenschlager, and reproved by Lot, Sturm, and Villani, to prove a generalized Brunn-Minkowski theorem on spaces satisfying curvature dimension. So my plan is to introduce curvature dimension tomorrow. Okay, right now we're still doing everything in Rn. So let me just give you kind of a baby version, which has been known since the 70s. Let's see how much time I have. I didn't plan. Okay. So let me just use this principle to prove a theorem in Rn, which is due to Borel, Braskamp. So this is, sorry, independently from the same year. This is everything in Rn. So here's the theorem. So let U have an absolutely continuous measure in Rn. Okay, and we have a parameter capital N, which is between minus infinity. It's in this kind of strange range, but you'll get used to it. This is 0, not 1. So little n is the dimension of my space. Capital N is this parameter. Then the following are equivalent. Okay, so 1, this density is concave on its convex support. first property. Okay, notice I'm multiplying by this coefficient. This is just because I'm also allowing negative values. So then kind of the sign here does play a role in if you're testing concavity. And the second property is that for any two sets, A and B, let's say compact sets, but it really doesn't matter. It's any Borel sets. But at least compact sets will make sense quickly. I'll explain what I mean, but when I write the sum of two sets, this is bigger than like this. Okay, this is kind of a Brunn-Minkowski type inequality. Okay, so that's the theorem, which I quickly probably just basically leave you various parts as exercises, but some remarks. So what I mean by A plus B, this is Minkowski sum. This is all points of the form A plus B, where A ranges in A and B ranges in B. Okay, so for instance, if these are compact set, this set is compact. It's a continuous image of a compact set. But also, if these are just arbitrary Borel sets, this turns out maybe not to be a Borel set, but a Lebesgue measurable set. So no problem testing this measure. Okay, so this is Minkowski sum. Second remark is that the case of capital N equal to little n, well, this formulation only makes sense if psi is just equal to a constant, let's say 1. And this means that I'm just talking about Lebesgue measure. And then the statement is that the Lebesgue measure satisfies this. So I'm just testing the volume of this interpolation of these sets. And this is the classical Brunn-Minkowski theory. Brunn-Minkowski theory from the 19th century. So this is a generalization of the Brunn-Minkowski theorem. The case when capital N is equal to infinity is also covered. This is due to Prekopa and Lendler. Prekopa. This. Lendler, this is the case of N capital infinity. And then this guy is interpreted in the limiting sense, meaning that you get actually a geometric average. When you take N to capital N to infinity, this is what you're going to get. So this is the interpretation here. And also this is, and here this amounts to log of psi being. So if log of psi is concave. Okay, so that's again something from the 60s and 70s. And finally, note that when N is negative, this still applies, just the sign get reversed. And this is why it's typical to put the 1 over capital N on the left-hand side, but to make it work for negative values of N, you have to put it on the right-hand side. So inequalities are reversed. And this explains this kind of strange factor that I put before my, strange scalar factor that I put before my function. Okay, so let me give you an idea of the proof. This is actually just motivation, so I didn't want to spend time on this. I see I'm already spending too much time on this. But still, let's complete the exercise. So this is going to be basically a guided exercise for you, okay? So 2 implies 1 is the easy thing. You just test, if you know 2 and I want to get 1, so you just use A equals, I have some point x. I take a small ball of radius epsilon, but actually I want to multiply by some factor. And I have another, for my set B, I'll take another point y plus some ball of radius epsilon times some factor b. And I'm going to take the limit as epsilon goes to 0, and then optimize. So this, by Lebesgue differentiation theorem, will just converge to the relevant densities. And then I still want to optimize on the values of little a and little b. Okay? If you want to get the right power here, you see, this is the power of 1 over capital N. This is the power of 1 over capital N minus little n. And that's the role of this optimization here. Otherwise, you'll get the wrong power. I mean, you get a weaker result. So this is just an exercise by invoking Lebesgue differentiation theorem. What about 1 implies 2? That's the interesting direction. Let me just do it for, prove for capital N bigger than 1. Okay, bigger than little n, if you will. For negative, it's the same, only all the inequalities get reversed, so you can just figure out. It's exactly the same proof. Okay, so what is the idea? So again, we're going to use the Bernier map. So if, just recalling again, if T is equal to grad phi is the Brunnier map from mu naught equals some density to mu1, some other density, phi naught times mu and phi 1 times mu. Okay, and I introduce these interpolating guys. And again, I call the densities phi, interpolating densities phi t. Okay, I guess just as above. Okay, let me give you the kind of plan B, which is the quick version. So this is on the opposite page. So step one. Step one in this guided exercise is show that the claim, meaning number 2 here, show that this follows from the displacement convexity of T goes to, I'm going to use this entropy functional, mu sub T with respect to mu, which is minus, I'm giving you the definition, it's minus, you take the density, interpolating density, to the power of n minus 1 over n, d mu. Okay? And basically, so just hint, so I claim that it's enough to show this. It's enough because I can use the densities phi naught equals. So I just take the unit, sorry? Thank you. Thank you very much. Thanks. Yes, thank you very much. Thank you very much. Yes, definitely. Mu 0, I called it. Oh, yeah, d mu. That's right. Thanks. So I want to have 2 probability measures. So I'm taking this measure restricted onto A and renormalizing to get a probability measure. Okay, and then just use the observation that minus TA plus TB actually contains the support of mu sub T. Okay, because if you're taking your set A and your set B, then of course, if you're using this interpolation, then it's contained in all possible ways. If you, so this is a particular way to get a point here. It's just you take interpolating of this point x and this point t of x. Of course, this is a subset of taking all possible points x and a and y and b and using the interpolation. So the support of mu sub t is certainly a subset of this Minkowski interpolation. Okay, and then you can use Jensen's inequality to claim that the measure of the support of this even smaller set is bigger than minus the entropy of mu. Okay, so that's kind of the first step that you need to do, and this is the hint. It should be enough to do it. Okay, step 2. Okay, step 2 is to show, just using a, so let me assume that everything is smooth. I'm not worried about rigorosity here. So show that basically what we're trying to, this entropy, let me forget about the minus sign here, because instead of showing that the entropy is convex, I'll show that minus the entropy is concave. Okay, so if you just do a change of variables, y equals t, everything here is, let's say, y. I make this change of variables, then the exercise is to show that, I mean, it's just immediate, is to show that this holds. And basically, this so this is your exercise, show that this holds. This means that if I want to show that this guy is concave, look at the right-hand side. The only thing which depends on t is this guy. So this reduces, showing the displacement concavity of this guy, to just a 1D analysis. I just want to show, so this reduces to 1D analysis, namely showing that jtx to the 1 over n is concave along, well, t goes to that, is concave along this 1D interpolation. Okay, so now while we have this, I just need to show you that this guy is concave. And for the grand finale of the proof, okay, here comes the part I'm nervous about. Let's see if this, well, I'll use this. No? Okay, here goes. Yeah, okay. Actually, I think I can raise this. I need more water, yeah? Well, the Jacobian, I mean, for every x, I just need to show to you now that this Jacobian, for any fixed x, this is a one-dimensional function in t. T is in the interval 0, 1. Okay? So it's, I just need to show you that the Jacobian along these one-dimensional rays is, the Jacobian along these one-dimensional rays is, to the right power, is concave. Okay. I don't think I'll have a career in shield washing. Okay. Yeah, you have a car? Yeah, are you here with a car? Oh my God. Okay. So now it's too much water. Okay. Okay, so step 3. Oh. Any question about my technique? Or? Okay. The first row may get wet. Yeah, as I say. Okay, so now step 3 is just to note that the Jacobian here can be written, and this is a kind of recurring theme, as a product of a geometric Jacobian coming from the geometry of your space and a weighted Jacobian. So the geometric Jacobian, remember, we're doing everything. Yeah, I should have said that JT is actually JT is Jacobian of this map with respect, that's important, with respect to the measure mu. Okay, everything is not with respect to Lebesgue density, but with respect to the underlying measure mu. So therefore, this means that it's Jacobian. I can write this as a geometric part, which is just the determinant of the derivative of this thing. So it's the determinant of 1 minus t times, okay, derivative is identity plus t times the second derivative of phi, which is great because phi was convex function, so this is non-negative. Okay, so I like this guy. And the weight, and the weighted part is just the ratio of the densities, because I'm doing everything with respect to mu, so I need to take the density of mu psi at the point t, at the destination point, and I divide by the density psi at the origin point. Okay, and then the Jacobian is just the product of the contribution of the geometric factor times the weighted factor. And now it remains to say that this guy, to the power 1 over n, is concave, thanks to the fact that the determinant to the power of 1 over n is indeed concave on the class of positive definite matrices. If you've never noticed this before, then it's a very nice exercise. Basically, you can reduce to the case that both matrices are, let's say, simultaneously diagonalizable, and then you diagonalize them, and then you use arithmetic geometric mean inequality. So this is a very nice property of determinant to the power of 1 over n on positive definite matrices. So I'm really using here the fact that this guy is concave. So this guy to the power of 1 over n is concave, and the other guy, the weighted factor to the power of 1 over capital N minus little n, is also concave. Why? That's our assumption, because psi itself, so this guy is just, we're just interested in the behavior as we change little t. So this guy's fixed. It's just a scalar. I don't care about the denominator. And this guy is because psi to the 1 over capital N minus n is concave on any segment. on any one-dimensional interval. So this is a one-dimensional interval in Rn. This guy to the 1 over capital N minus N is concave. So these guys are concave. And then you just use Hölder's inequality. That's part of the exercise. Hölder's inequality means that when you take the product, then this guy to the 1 over the sum of the denominators is concave. And that's step 3 of a proof. Once you show this, then you trace back, you show the displacement concavity, and step 1 tells you that you proved your Brunn-Minkowski inequality. Okay, so basically that was supposed to be just motivation. It took a bit too long, but this is how you can use optimal transport, modulo some technical details, to reduce some problem in analysis or geometry, Brunn-Minkowski inequality, to a one-dimensional problem. This is the reduction to 1 dimensions. Just check, this is McCann's principle. So this was supposed to be motivation, and now we're going to leave optimal transport. It has some advantages, but also the traditional point of view, I think, has some disadvantages, or at least, some restrictions that have yet to be overcome. And now, let me tell you what I mean by one delocalization. Okay, so if this was a bit too fast, I'm sorry, but this was just basically motivation. And I hope you got something out of it. But anyway, let me introduce our setup, or at least kind of the lowest common denominator to our setup. So we're going to work basically in the smooth setting. There's no funny business. So what we do want to work with manifolds. So this will be, so M is going to be an n-dimensional smooth, say, connected Riemannian manifold. I don't necessarily assume that it's oriented or that's complete. Okay. The induced geodesic distance is exactly what you expect. Okay, so it's just the infimum over all paths connecting points x and y, and you calculate the length of the derivative of the path. So gamma A is equal x, and gamma B is equal y. Okay, and that's the geodesic distance, and we are going to assume that our manifold is geodesically convex, meaning that any x and y, so this is bad for us, right? This is bad. This is good. So for any x and y, there exists a distance minimizing geodesic connecting x and y. Okay, so what's a geodesic? It's just anything which is, let's say, locally distance minimizing path, or if you want, satisfying the geodesic equation, which is just first order OD. Okay, so that's kind of usual things. And now, as is common, we're going to introduce, of course, a measure. This gives me a metric space structure. I want to have it weighted. So I'm allowing to use a density psi with respect to the Riemannian volume measure. So the assumption is that psi be positive and continuous. That's kind of the minimal assumption that we'll want. For some applications, we'll actually want to assume more about psi, that it's C2 smooth. But let's assume that it's just positive and continuous. And lambda g, this is the volume measure. Not necessarily a form, so I don't assume orientability. So in local coordinates, this just means that it's square root of the determinant of g ij dx1 dxn, some local coordinates. So the point is, I'm not taking wedges here. So I take the absolute value, if you will. Okay. Again, it's not. I really don't care about these details, but if you want to know, you don't really need orientability. Okay, so the a nightmare again. Okay, let's see. Are there any questions? It's a good time for questions. Oh God. Yes, I should practice. Okay. Okay, so here's the definition. So we'll say that mu, if I can write mu as this type of integral, so it is called this integration. This is called the disintegration of mu. If, first of all, so this is just some auxiliary, not too important, let's say complete measure space. Okay, so lambda is a set of indices, nu is some f, whatever, some sigma algebra measurable measure, complete measure. But more importantly is that for any, let's say, Lebesgue measurable set A in our space, of course, this definition makes sense in greater generality on any, let's say, metric measure space, but I'm just working with this smooth kind of situation. So Lebesgue measurability is still defined. You know, it's I don't know, take your favorite atlas, you pull back Lebesgue measurable sets on our end via your charts, and this is the sigma algebra generated by this thing is called the Lebesgue sigma algebra on your manifold. Okay, so for any Lebesgue measurable set, I would like the following function. I would like two things. First of all, I would like the function alpha going to u sub alpha to be defined, well, mu almost all alpha, and is f, and this map taking the index alpha to the measure, the mu alpha measure of A, is indeed f measurable. Okay, so this is just some to make sure that measure theory makes sense. But more importantly, I would like that the measure of A, now I have an f measurable function, I can integrate it. I would like that for any measurable set, I can get back its measure just by integrating it. I don't know what to do to stop this squeaking sound. Sorry. Okay, so kind of a standard definition of disintegration. Okay, kind of obvious. And moreover, we'll define a localization, a 1D localization of mu is a disintegration so that there exists a set, a full set of measure of indices such that, well, first of all, I would like that for any alpha in this full set of full set of indices, mu alpha is what we'll call a one-dimensional needle. Sorry? Ah, okay. Yeah, some expert tips. Okay, so we'd like this to be a one-dimensional needle. What does it mean? Just I want it to be supported on a distance-minimizing geodesic. Supported on a distance-minimizing geodesic gamma alpha from some interval L alpha, let's say open interval, let's say open subinterval of the real line to our manifold. So this is my geodesic, meaning that, of course, supported here, I just mean that. So I don't distinguish between gamma alpha, between it as a map and as its image. Okay, so gamma alpha could be both a map and its image. Okay, it's kind of standard abusive notation. So mu of alpha A intersected gamma alpha is equal to that. In this sense, it's supported on gamma alpha. Okay, and second, and actually very importantly, is that all of these guys are disjoint. Okay, and that's a very, so in principle, a disintegration could be something like this, right? So it could be, you know, I'm taking the Fubini, but I'm doing it like n times with the, you know, in all possible directions. Okay, that could be a disintegration of Lebesgue measure, but no, that's prohibited. So disintegration could be something like this, just the density dx1, a localization, sorry, could be something like this, dx1 in one direction, or polar coordinates, you know, r to the n minus 1 dr. That's fine, but these are kind of trivial examples, right? You would like to get something more interesting. And we'll see that actually already having this one delocalization is enough. Only these two properties are already enough for the needles, for these one-dimensional measures, to inherent curvature dimension properties from the big space onto this one-dimensional needle. Okay, I'll define curvature dimension hopefully tomorrow. Tomorrow. But anyway, we'll see that already this is enough to inherit these curvature dimension properties. And of course, a second remark is that, of course, there's no uniqueness, okay? If I have such a representation, let's say that mu is a probability measure, of course, I can multiply mu alpha by some measurable function, depending on alpha, and divide the measure. So there's no unique way to represent it. So for instance, if mu is a probability measure, then I can always assume without loss of generality that all of my, or almost all of my mu alpha are probability measures by renormalizing them, because with probability 1, they're non-zero and finite mass, right? So I can renormalize them and put everything inside the nu, okay? So this means that if, this will be my standing assumption. If mu is a probability, then almost all needles are themselves probability measures, and nu turns out that nu is also a probability measure, because the total mass has to be integrated into 1. If I test the measure of the entire space, mu of m is equal to 1, then this is integral of 1 d nu, so this means that nu itself is a probability measure. Okay, so this is just obvious remark, but it has to be said, yeah. Yeah, disintegration, but not just that. Oh, okay, I see what you mean. Yeah, sure. So any partition, measurable partition in the right sense, there are measure theoretic theorems to the extent that any measurable partition will induce, let's say, one delocalization. Well, not localization, because for localization, I want these guys to be supported on geodesics. But let's go back here. Will induce, you know, this property without the first item. Okay. Yes. No. This will be exactly the situation. In fact, much more. It will be given by kind of almost differentiable partition in applications. Yeah, lambda is at the moment, yeah, you can think about this as a partition map, but for me it's just an arbitrary, for me it's a tool, so it's like an arbitrary index set. Yeah. Okay, so at this point, this is nice, but still not completely useful for applications. So to make this notion useful, we'll need an extra condition, which was already going to be adapted to a specific problem. So definition, last definition, is that our local, let f be some L1 function with integral 0, then we'll say that a 1D localization is f balanced, is called f balanced if for nu almost every alpha, the integral of f d mu alpha is equal to 0. Okay? If, with respect to this function f, actually each of these one-dimensional needles integrates to 0. Well, nu almost everywhere, of course. Okay? And now, I will spend the rest of, okay, I planned for this to be a bit longer, but I guess I'll continue tomorrow. I'll spend the rest of my time convincing you why, if we had such, if we had a machinery so that given an f in L1, which integrates to 0, gives us an f-balanced 1 delocalization, that would be amazing. That would reduce many of our problems to one-dimensional problems. Okay, so let me give you many examples, and you know, this is basically this is the maybe most important part of this mini course because it's supposed to serve as motivation to get interested in this. So let me show you how you can take essentially your favorite geometric or analytic problem and basically reduce it to a one-dimensional analysis. So, any requests? What kind of problem do you want me to reduce to one dimension? Okay, I have a specific order in mind. Is that it has to qualify under geometric and analytic. Okay, so let's start with Brunn-Minkowski. Okay, so assume that we have such a machinery. Okay, so reduction of Brunn-Minkowski type inequalities to 1D analysis. Okay, we did the one-dimensional Brunn-Minkowski with optimal transport, so let's continue with this theme. Okay, so what we want. Let's say we want to prove, it'll be a completely different proof than what we saw before. So maybe it's interesting to compare. Let's say we want to have this type of inequality. I don't care what this function capital F is. I just need a few properties. This is the type of Brunn-Minkowski inequality that you will see kind of in applications. So I have to tell you a few things. So F, in the first two coordinates, I need to assume that it's homogeneous. It's one homogeneous in both the arguments, in V1 and V2 together, I mean, in R2, and monotone in this D tilde. So D tilde, just in applications, could be either the Hausdorff distance between A, B, or kind of the anti-Hausdorff distance. So either it's the supremum over the distance between A and B, or A is in A, B is in B, or it could be actually the infimum. This is how it appears in applications. Okay, so you'll see in the sweet and nice proof. I mean, okay, sometimes you need to use that, sometimes you need to use that. Okay, that's how it appears. Okay, let's say you want to prove that, and of course I need to tell you what is this. We're in the Riemannian setting, so what am I talking about? What is this? This is a linear operation, the way I defined it before. So by this, I mean that this actually makes sense on any geodesic space. When I write something like this, I mean just via geodesic interpolation. So it's all points Z in my manifold or on my metric space, so that there exists X and A, and there exists Y and B, so that the distance between X and Y is equal to the distance between, I'll draw a picture in a second. So just what do you expect? So if this is A and this is B, I want to find a point X here and a point Y here, so that if I connect them and use this kind of T1 minus T interpolation, then I just take the collection of all points Z that I can get in such a manner. Okay? So I take the collection of all such points. Okay? And this is how I define this geodesic interpolation between the sets A and B. So this is a Brunn-Minkowski type inequality. Let's say I want to prove this. Okay, what can I do? If I want to prove this, so given specific A and B sets that I'm interested in, what we'll do is I'll define the following function, which obviously integrates. This obviously integrates to 0, okay? And if you give me such a machinery, I'll use it. Let mu be a balanced disintegration. One D localization, we said, yeah. I have to use my own notation, right? Thing to do. So, you know, so I have my set A here, I have my set B, and basically, I have a way to kind of split my space into some measures supported on these needles, so that the integral of f d mu alpha on every needle, I preserve the proportion, relative proportion of my sets. So if I knew that mu alpha for each of these one-dimensional guys, if I look at the interpolation, by the way, so someone should tell me when to stop. I'm not sure how this works because we have, so tell me when. 5? Okay. So if we knew that for these one-dimensional guys, I could write such an inequality with this functional f, depending maybe on t, and depending on d tilde of A intersected gamma alpha, B intersected gamma alpha. Okay, let's assume that someone tells me that. Well, thanks to the fact that all of these guys integrate to 0, d mu alpha, this means that I know that I know that the relative measure gets preserved. So I know that mu almost for every alpha, I know that mu alpha preserves this ratio. Okay, so now I can use this one homogeneity to pull this guy out. So this is still an equality. Okay, so still this is an equality. I'll be an inequality in a second. I'll pull out the mu alpha like this. And I'll write f mu A mu B, like that, T. And now, this is the role of this D tilde. Now, depending on the application, so A intersected gamma alpha, of course, the Hausdorff distance or the anti-Hausdorff distance can only increase or decrease if I move from these sets to D tilde of A comma B. Okay, so I know instead of just looking at the distance from these guys, I can look at the distance between the whole space. So, of course, if f is monotone in the right direction, I'll get an inequality in this going in this direction. Okay? And now, it remains just to say, oh, God. Yeah, I'll finish there. Let me show you the reduction. I need, I guess, one last time with this instrument. So if I knew this, so everything is, assume that I have this inequality, which is a one-dimensional analysis. You would agree, right? This is a one-dimensional guy. Assume that I could do this. Well, the big set, of course, interpolating between A and B, well, it's a smaller set is just interpolating between each of these guys separately. right? Because the entire set would be if I use, let's say, gamma alpha and gamma beta. I would take all possible points in my set and calculate all possible midpoints, T1 minus T midpoints. But this is a very specific way. I'm just doing the T1 minus T interpolation along these one-dimensional needles. So this is a smaller set. So if I calculate the measure here, this will be smaller than the measure of this guy, okay? Which is just, if I let's use the fact that this is this integration. I just integrate over the individual guys, because, of course, mu alpha is only supported on these geodesics. So they just care what happens to the intersection of this set with gamma alpha. So I just care about what's going on here. I would use my 1D. This is my 1D analysis that I had before. This is my 1D analysis. And what do I get? You see, this guy doesn't depend on alpha. This guy doesn't depend on alpha. It just pops out of the integral. The only thing that depends on alpha is this. So I would get this guy, which is constant, times this integral d mu alpha, but this integrates exactly the measure of mu alpha. This is just one, right? This is the property of my this integration. The integral of mu alpha a is equal to the integral of a. So this is just one. And you see I get my desired inequality just by, if I could prove this one-dimensional analysis. So just a second. So of course, I miscalculated the time, but I guess I'll continue tomorrow by showing you that exactly the same program can be done for doing it for Poincaré inequalities, Sobolev inequalities, isoparametric inequalities, various tricks of that. And I guess the plan is then to introduce the curvature dimension condition. Okay, and then this is nice. This is a fantasy. How can I really construct such localizations? Yes, I can. There are various different ways. I guess I will maybe skip one of these methods, but I'll spend the second half of the course, let's say, to show you, after hopefully you've been motivated enough to get interested in this, how to construct such localizations. Okay, so yeah, sorry, there was a question. Just because I wanted to, let's say for some reason your Brunn-Minkowski inequality, and this happens if you look at the inequality by, Cordero, Schmuckenschlager, and actually more specifically in Sturm's paper, let's say, you will see that it also depends on some distance. Okay, now I want to pass from A intersected gamma alpha between the distance of these guys to the distance of the big sets, because I don't want a term which depends on alpha here. So depending if you use the Hausdorff distance or the anti-Hausdorff distance, there is a monotonicity here, and I did assume that my functional f is monotone in the right direction. So you just, yes, but it doesn't depend on alpha. So I want to prove this inequality, and certainly it may depend on the distance. The general Brunn-Minkowski inequality that you will see, let's say, in Sturm's paper, will depend on the either Hausdorff distance or the anti-Hausdorff distance, depending if curvature is non-negative or negative. Okay, so I want to allow this. We didn't see this in the previous example in Rn because it wasn't needed. So you can just forget about this term. It just wasn't needed. So you see, it's a different proof. Instead of kind of looking at a strange entropy functional and integrating that to get your Brunn-Minkowski inequality, here it's much more straightforward. You really you disintegrate your space, preserving the ratio of the relative measure of A and the relative measure of B. And then when you do the integral, there's no Jensen inequality, there's no funny business. It just integrates out as a constant factor. Okay, and this will be a recurring theme. I guess I'll continue tomorrow with this theme. Yeah. Okay. So in general, for any, the last thing will be the most general one. For any functional one, you need some properties of the measure too. There's just a small technical assumption. But at the moment, it works for any weighted Riemannian manifold satisfying a small condition. Okay. I think recently there has been some extension of this method to more general metric measure space settings. So we'll hopefully start to give more details as we progress.
Okay. Are there
Oh yeah, Borel-Bascom maybe was 70s. I mean. Okay, so you can, originally, there are two proofs. Okay, Brunn-Minkowski inequality, yeah, sure. It's a good historical comment. So Brunn-Minkowski inequality goes back to some level of rigor to the 19th century, okay? Brunn-Minkowski worked on this in the late 19th century, okay? Maybe a final proof is attributed to maybe beginning of 20th century. Some small things had to be corrected, but for convex sets at least, the proof is circa 1900, and then for general sets, compact Borel sets, maybe this is due to Lusternik, actually 1930s. And then there are many proofs of that. So Borel, what Borel did is generalize a proof due to Oman and Hadwiger, which is, there's a very nice proof of Brunn-Minkowski by doing it, like assuming that your set is a union of, let's say, boxes, okay, just, n-dimensional boxes, and then doing induction on the number of boxes. So he generalized this proof. Braskamp and Lieb did this in another way. Basically, all of these inequalities follow from, if you just need to prove it using some Holder arguments for some specific value of capital N, and you can do it by induction. Because there's also a proof, there are like zillion proofs of Brunn-Minkowski. One of these proofs is by induction on dimension. So they do it in dimension 1 and induct on dimension. Okay, I mean, you certainly don't need, there are many, many proofs. It's, a topic for a whole different course, and a zillion proofs of proving Brunn-Minkowski and its variants. I deliberately wanted to show this proof using the optimal transport machinery. I don't claim this is the shortest proof at all. Okay, right. But I wanted to do the one, you don't see the one-dimensional analysis in all these proofs. That's why I chose this proof. Yeah. That would be simpler. That would be a shorter proof. I agree. I wanted to deliberately show you the kind of difference and the similarity.